Hello again. This is the latest in my little series on SSL certificates and cryptography type concepts that are necessary for that. And I hope you guys are familiar already with I guess various things like public private key encryption, digital signatures, hashing, etc., etc. They're all covered in quite a lot of detail on previous videos in the series. So this is, I guess, getting towards the business end of the whole SSL certificate system. And the diagram, it looks a bit busy, but I want to go over it in a lot of detail, and hopefully the reason I put it on one diagram was that I want everybody to see this over the course of the video, understand it, and then realize that everything you really need to know about the certificate chain is actually on this diagram in one place. So it looks a bit intimidating at the start, but hopefully all will become clear. So in the previous video we talked about man-in-the-middle attack, and essentially a man-in-the-middle attack was it was concerned with being presented so let's say Humpty's client computer being presented with an SSL certificate or with a public key that apparently is supposed to belong to the bank, but in actual fact is belonging to a man in the middle who was sent their own public key instead. So how does Humpty here, who's accessing his online banking, we're using the actual screenshots of the HSBC SSL certificate chain here. So let's say Humpty is banking with HSBC, and his client computer basically is accessing the HSBC website, the secure website, and that computer or that server sends back this SSL certificate, right? And that's the actual certificate that HSBC are currently sending back. hsbc.co.uk are currently sending back to any client that connects to them as of now. So looking at this, so now in this SSL certificate, basically, which is a holder for the public key, as we've mentioned in previous videos. So the public key is down here, right? And then if you remember the video on RSA, so public private key encryption, the public key is actually composed of two numbers, an exponent and called a modulus, right? So those two numbers together, this is a 256 byte number, so it's a huge number in binary, and it's expressed with these hexadecimal characters, which I explained in the digital signatures video. So those two numbers together, they form the public key, right? Which is what we sort of diagrammatically represent as this green public key. And hopefully you guys are all familiar with my silly little diagram conventions by now. So the bank has this public key, and it's sending it to Humpty Dumpty wrapped in this certificate document. And Humpty says, "Okay, great. How do I know that this public key actually does belong to HSBC, right?" And that is all done using what's called a certificate trust chain, right? And I think the best way to describe it is to describe the workflow by which this certificate document is first created. Where does it come from? How is it generated? And that hopefully will explain how the trust chain works, and how ultimately Humpty over here can trust that this public key belongs to HSBC. So I do realize this video is not particularly straightforward. I probably will end up repeating myself a few times, and I'm going to see how short I can make it. But I think the most important thing is that if you can spare 30 minutes to watch this and persist with it, then hopefully you will understand it. For those of you who are finding it boring or repetitive, you probably don't need to be watching it at all. So anyway, that's a little disclaimer. Anyway, so let's talk about the life cycle of an SSL certificate. So the HSBC, when let's say they first go into business and they're setting up their website, and they say, okay, right, first thing we need to do is we need to generate a public and private key pair, because we want our clients to be able to communicate with us securely, right? So the HSBC web server will generate, using some software, a corresponding public and private key pair, which are basically those numbers. One of them is the private key, and the other numbers are the public key, which is the exponent and the actual public key here. So it generates essentially three numbers, and they all have this close mathematical relationship with each other. Now, what the problem is, HSBC can't just generate, or they can't just really generate their own certificate and say, right, we're HSBC, this is the public key that I've just generated, here's our address, here's our etc., because any man in the middle receiving a certificate from HSBC knows that could have been done by anybody, right? So anybody, I could do on my laptop right now, I can say, right, okay, generate a public-private key pair and create an SSL certificate with the name HSBC, and then I can set up my own website and install that certificate on my local system. So the point is, we need a way for HSBC to prove to the outside world that this public key that they generated actually belongs to them. Okay? So how does that happen? Well, it happens via what's called a certificate authority, or more specifically, a chain of certificate authorities. But in the simplest case, let's keep it simple to begin with, it's a certificate authority, which is an external trusted organization or authority whose job it is to verify and issue valid SSL certificates to bona fide organizations. Now, the extent of the validation depends to some extent on which authority you're using, and what normally happens is that the more expensive the certificate, because you have to pay these authorities for the certificates, the more expensive the certificate, the more validation they will do on your details, which in turn means that clients who see this certificate when they're browsing your site will actually have more trust in the actual certificate, right? So back to the life cycle. So the bank generates the public-private key pair, then it fills out a special electrical form, and that's called a CSR, Certificate Signing Request. And that certificate signing request is basically a form that contains this information, like the organization, the address, the common name, which is the effectively the domain name, the website, and all this kind of stuff, the business category, this kind of stuff is all in that initial form that HSBC fills out. Okay, it also includes the public key in this in the certificate signing request, and that's one of the things it has to fill out. Then what it does, just as an extra safeguard, it actually will sign that certificate signing request with its own private key. Now, hopefully you guys are familiar by now with what I mean when I say sign. I'll just go over it in 20 seconds. Effectively, you take the completed CSR, including the public key, you hash it, using SHA-256 hashing algorithm, and then you encrypt that with the private key that corresponds to the public key that the bank is inserted in the CSR, right? So then they'll basically append that signature to the end of the CSR, and then send all that across to the certificate authority. So because we're using a real life example here, let's say we are actually HSBC are applying for this new certificate from it's semantic class 3 EV SSL certificate authority, and then you can see. Well, we'll go into more details about that in a second. So let's just call it semantic. So the bank sends this CSR to semantic. The first thing that semantic are going to do is they're going to check the signature, right? So and what that means is that they're going to take the signature at the bottom of the CSR. They're going to decrypt it with the public key in the CSR. Remember, the CSR in itself is not encrypted. It's just the signature is basically the encrypted hash of the certificate, right? I don't want to go too much into CSR, so I'm sorry if I'm diverging a bit, but as I said, the aim is to basically make everyone who watches this and sticks it out have a pretty solid understanding of the life cycle of these certificates. So semantic, get the CSR, there's no certificate yet. They get the certificate signing request, CSR, they look at the signature, they will decrypt it using the public key provided inside the CSR, right? And then what they'll do is they'll hash the CSR and make sure those two things line up. So it's a very, very standard digital signature validation process. And what that means is basically that it proves to semantic that the public key in the CSR was owned by the people who actually signed the request, i.e., who sent the request, right? So, and that's a very similar scenario to the actual certificate chain validation that goes on later in the video. So, what happens then is the guys at Semantic, or whoever that certificate authority might be, they start then validating and doing some checking to make sure that HSBC, the people who have just sent them the certificate, really are who they say they are. And they do all kinds of things from phoning up people at the organization, verifying that the address of the organization is correct. So if I just apply for a certificate for HSBC as a rogue, and I gave my home address, then that would quickly be snuffed out at this stage. Semantic will say, sorry, we're not going to issue a certificate for HSBC to that address. That's not the correct address. Anyway, so after all that validation happens, what Semantic do as a certificate authority is they take the information in the CSR, so all that stuff here about that HSBC filled in, and they create a document called an SSL certificate from that, right? And we've talked about SSL certificate. That's the actual time when this SSL certificate gets created. It gets created by the certificate authority, containing the details in the certificate signing request, and then you can see the contents of the. Let's just quickly go through some of the contents. That this is the actual SSL certificate used by HSBC currently. You have issued by, so Semantic will say, okay, it's issued by us. There'll be an expiry date after which any browser or any client who encounters this certificate will say, this is no longer valid. And then it has all this cool information here about HSBC. So the domain name that this applies to. So I'll just mention here, probably mention later on as well. If a browser basically is accessing a website and in the address bar, the domain in the address bar does not match the domain in the SSL certificate, then that's one scenario where the browser will or the client will basically reject that certificate and throw a warning or whatever it's configured to do. Okay, so that's all the stuff that HSBC would have submitted in their CSR, and that's what the Semantic guys would then include in the SSL certificate. Then Semantic will include a section in the certificate which is about themselves, right? So they say, okay, we are issuing this, and this is who we are. We are Semantic Corporation, and basically we this is a sort of a unique identifier for them as an entity, Semantic Class E. We're going to get into this quite soon in the video, but for now, let's just carry on going through here. I'm going to skip that signature algorithm. So this is basically, we've talked about SHA hashing, SHA-256. What it means is that Symantec are going to use a SHA-256 hash function in order to create the signature for this certificate. Right, now we'll get to that in a second. What else have we got? So, okay, down here in the certificate, as I said, the CSR that HSBC sent to Symantec obviously contained HSBC's public key. So Symantec will include that public key in the certificate, because at the end of the day, this SSL certificate is really only there as a kind of as a placeholder and a way to present the public key from HSBC to Humpty Dumpty's client in a way that Humpty can trust, right? That it doesn't belong to a man in the middle. So obviously the public key is a very important part of the actual SSL certificate content, and that's, to be clear, that is the public key belonging to HSBC, right? Who have obviously the corresponding private key that they generated right at the beginning, which will never ever leave HSBC server, right? It never, and that's very important. And then, if we look at the bottom here, the signature, this is probably, one of the other absolutely most important parts of this overall SSL certificate that we can inspect here. And see, I've tried to sort of keep, I know there's a busy diagram, but everything in purple represents basically the signature operation, right? So everything inside this purple box here in this certificate is hashed by Symantec when they issue the certificate, and then, so using SHA-256, so if you can see my mouse pointer here, the signature algorithm used is SHA-256. So over here, this mincer here, which is what we use to represent a hashing algorithm, Symantec are going to take this content that they've generated, put it through the SHA-256 algorithm, and then they're going to encrypt the hash with their own private key. That's really important. So Symantec have their own public key and their own private key, right? Just like HSBC have their own private key and their own public key. So Symantec, they take the hash of the certificate that they've generated for HSBC, they encrypt it with their own private key, and then that becomes the signature for the SSL certificate. Okay, so just bear with me. That entire document, which is basically everything inside the purple box plus the signature that Symantec have just generated, that is basically sent back to HSBC, and HSBC will install that whole thing on their web server, right? And that effectively is their SSL certificate that they've acquired, and they've had to pay Symantec some money for this service. What they now have is an SSL certificate, which is a document that contains their own HSBC public key, which is signed by another authority. So it's a bit like taking a document and getting it signed by a trusted witness, right? And then you can then present that document to everybody else and saying, okay, well, you can trust the contents of this document because this guy who we all trust has signed it and said, yeah, it's valid, right? So one really important point, I know I'm going to labor these points to the full, is this signature here is signed not by the private key belonging to HSBC, but by the private key belonging to Symantec, right? And that's it. So that's the end of the actual. My apologies for this interruption. So that's basically the installation and the acquiring of the certificate. Now, fantastic. HSBC now have their certificate installed. They can now, build their website. They can release it into the outside world, and now all they're loyal customers like Humpty over here can start doing their online banking, right? So that's the next use case. So let's get started on that. So when Humpty, and we've been over the basics of the SSL handshake and protocol in previous videos. When Humpty goes to hsbc.co.uk and logs in, and it goes to the secure site, which means it's going to be an HTTPS session, the first thing that happens is HSBC are going to send their certificate, including the signature, over the internet back to Humpty's client browser if he's just browsing on So then what happens is Humpty's browser has to decide, essentially, do I trust that the certificate that I've been provided containing the public key that I'm being told belongs to HSBC really belongs to HSBC? Because if going back to our man in the middle video, we know that it's possible theoretically for somebody to intercept this document being sent back and then potentially insert their own public key in here and then present that back to Humpty, and then if you've followed my previous videos, you'll know what chaos can ensue from then. I don't have time to go into it now again. Okay. So how do we know that this public key actually belongs to HSBC? How do we know that the certificate is valid? Well, the first thing they do, and it's all down to the digital signatures again. So the first thing that Humpty's machine, his browser, is going to do is say, right, well, I've got a signature here, as well as a document in plain text, right? Now, how do I ensure that this public key has not been altered en route from the server, right? So the first thing it does is say, right, take the signature. If you remember, this is bread and butter signature stuff. Take the signature, and basically, I am going to look at in the certificate, who is the issuer of the certificate, and so the browser is going to say, okay, so this certificate is issued by common name Symantec Class 3 EVB EV SSL CA-G3. Quite a mouthful. So what it's saying is, I'm being told that these guys signed this certificate for HSBC. Now I know that what that means is that they will have signed, this signature comes from them. So to validate that signature, what I'm going to need to do is to find the public key belonging to Symantec Class 3 EV SSL CA, right? And then once I get that public key, I'm going to decrypt this signature, right, which effectively is unlocking this box, right? And then that is going to give me supposedly the hash of the actual plain text portion of the certificate, as in the hash of the everything excluding the signature, right? So what it does, it says, right, I'm looking for the public key belonging to these guys. I'm going to take the signature. I'm going to decrypt the signature using the public key because it was encrypted using the Symantec private key. So I'm going to decrypt it using the public key. That should give me the hash of the certificate. Now then what I'm going to do is I'm going to look at the the signature algorithm. Okay, it's SHA-256. Okay, fine. That tells me Symantec used a SHA-256 algorithm when they created the signature. So I'm also going to use, as the browser, a SHA-256 to check the contents of the certificate. I'm going to hash this certificate, right? And then compare that with the decrypted signature. And those two things should match. If they don't match, what it means is that the document that I've received here is not the same one as that's basically represented by the signature. Remember, the beauty of hashing is that if you suppose, even if you so much as put one full stop here, the hash of this document is going to be totally different, right? So if I hash this document that I've received and it doesn't exactly match the decrypted signature, then I know there's a problem, and the browser is going to reject this and say this is basically not a valid certificate chain. It's going to ask you whether you want to proceed, or etc. etc. So that's really how a man in the middle, for example, you can see already, and I am going to do a follow-up video on this to sort of expose and sort of talk about more about the implications of this, and what it means you can do and can't do, and whereabouts in this chain are the security threats, right? But I think that's definitely for a follow-up, and I just want to actually present the bare facts about the chain in this video. So now that's basically it. So if the man in the middle had actually modified this public key and put his own public key, then when Humpty gets it and his client computer hashes this document, it's no longer going to be the same as the decrypted signature, right? It's going to, because it's different content. And you might be wondering, well, can't the man in the middle change the contents of this and then sign it himself? So change the signature so it does match. Yes, he can, but we'll go into more details on that later. But the man in the middle, the evil guy, he is not a trusted signatory, whereas semantic are, right? So now, as you can see, this diagram has one more layer, right? And it's rather unfortunate in one sense that the HSBC example is a chain of 3 certificates. Often you just literally have one server certificate and then one issuer certificate, right? But that's the example we've chosen, and the good thing is that we'll get to explain everything in one place, right? So please bear with me. Now, Semantic themselves, they have an SSL certificate, right? Which has very similar fields, right? Subject, and then it has issuer. We're going to get to that in a second. Now the point is that when I mentioned the fact that Humpty's browser, once it verifies that this signature matches the contents of this document, and that Semantic really did sign this document because they were able to find the public key corresponding to Semantic and use that to check the use that to decrypt the signature. Once they knew that Semantic could be trusted, that was enough for them to say, right, go ahead, this SSL certificate is fine, this public key really does belong to HSBC. But we need to go into a bit more detail now about how Humpty was able to ascertain that this Semantic certificate authority could be trusted. Okay? Because who's to say, for example, that somebody could, pose as Semantic and insert their own, create their own certificate that says they are Semantic, generate their own public and private keys and then pretend to be Semantic, right? So, we're really getting into the nitty-gritty here. But effectively, what happens is that Semantic are an example of what's called an intermediate certificate authority. Okay? Now, an intermediate certificate authority, what that means is that these guys are free to issue SSL certificates to end users, and these end users will trust these guys, Semantic, because Semantic themselves are using an SSL certificate that in turn is signed by somebody who everyone in the world basically trusts. Right? I'm going to go over this a few times because I think at first glance maybe I didn't explain it very well. It is quite tough to get your head around to begin with, but I want you to imagine that there's one certificate authority, not semantic. And in this case, in this actual example, it's VeriSign Class 3 Public Primary Certificate Authority. So primary certificate authority, and then you see the words here, root certificate authority. Now, this certificate authority is actually hardwired into all major browsers and some operating system, depending on what operating system you're using. It's actually hardwired in there. So when you install Internet Explorer or Google Chrome or whatever, if you go to the settings in that browser, you'll see a list of trusted, what's called root certificates. And the chances are this certificate here will actually be, by default, embedded and into that list of trusted root certificates. Okay, so what that means, okay, is that I don't need to, manually go and get my own list of trusted root certificate authorities. It means that out of the box, these browsers are configured to, by default, trust any certificates that have been issued by this certificate authority or any children of those certificates. Now, we're going to go in. You can probably see from the diagram here what I mean by children, because you've got this issuer-parent relationship. So anything in orange here represents a parent-child relationship, where the issuer of one certificate represents the subject of its parent certificate. Okay, so I hope I'm not confusing too much, but hopefully by repetition and incessant rambling, things will get more clear, right? So imagine, and let's look at what's going on down the right hand corner here. So Humpty Dumpty has a machine that is running, let's say, Google Chrome, and that installation of Google Chrome, by default, out of the box, when he bought the computer from scratch, had already had this certificate installed in it, in the browser, right? What that means, so let's have a quick look at this. I hope you can see it properly. So it's got the same fields. It's an SSL certificate. Subject name is VeriSign, so VeriSign Trust Network. You can see the now the key point here is that they didn't get this certificate from anyone else. They issued it to themselves, right? And the reason is that they are the root of the trust chain. They don't need to be trusted by anybody else, because everybody in the world trusts them already, right? So these are the only guys who can actually say, right, I'm generating my own SSL certificate, and I'm going to sign it myself. Now, what does that mean when I say I'm signing it myself? Because self-signing is, you're going to hear it over and over again in this field. Self-signed certificate means that you take your certificate, right? So including your subject, your issuer, your public key, your expiry date, all that cool information about your SSL certificate, and you're going to hash that using SHA. Okay, this one is actually using SHA-1, which is supposedly on the way out. So we'll do a separate video on that as well. So in this case, they're going to encrypt it. Sorry, they're going to hash, not encrypt. Very important. They're going to hash it with the SHA-1 algorithm. Everything inside the purple box, right? Then they're going to encrypt the hash with their own private key, right? Their own private key, not somebody else's private key. So they're not going somewhere else to say, guys, can you check that I really am VeriSign? Can you call me up and make sure that I'm at this address? And no. These guys, everybody trusts them. They're the only people. It's like license to print your own money, or that's probably a terrible analogy, but they are allowed to sign their own certificates by hashing the certificate and then encrypting the hash with their own private key, right? That's really important. Anybody else is free to do the same. So I can generate my own self-signed certificate on my own computer for any website I want. The trouble is that this certificate that I generate will not be trusted by browsers. They don't know about me. They don't know about my certificate. These certificates here are deemed so trustworthy that they are actually hard coded into any browser or operating system, if it's a if it's a Linux server or rather JVM, if it's a all kinds of different clients. The key point is they're hard coded into something called a key store, and what it means is that any certificate received that is a child, either a direct child or an indirect child of one of these root certificates, so trusted root certificates, is deemed trustworthy by that client. Okay. Now I think let's just go over the parent-child thing again. In an SSL certificate, two main sections are the subject, which is the information about who this SSL certificate actually belongs to, and then the issuer. So who is responsible for actually providing the certificate, verifying, validating the details of the subject, right? And then signing the certificate. So who signed it? Because remember, you don't normally sign your own certificates if you want them to be actually trusted by other people. Okay, so the issuer is referring to the certificate authority who issued your certificate, and that certificate authority also has an SSL certificate that represents them. Right, it's really important. So semantic class EV SSL G3, that certificate authority is represented by this SSL certificate, right? Because, well, not because of anything, but because what I'm saying is that the issuer of our HSBC certificate corresponds to the subject of its parent certificate. So that's how we know that this one is a parent of this one. In turn, what I'm trying to say is that the issuer of Semantic's SSL certificate was somebody else. Because Semantic themselves, these guys, they're not deemed kind of super trustworthy enough to be hard-coded into all these browsers like the trusted certificate authorities are, right? So it's called an intermediate certificate authority. So these guys, they are basically their certificate requires signing by a trusted certificate authority, right? So these guys, this certificate here, therefore, has a parent certificate, which is VeriSign Class 3 Public Primary Certification Authority G5, and that corresponds to the subject of the parent certificate. And so this root certificate authority up here, which is VeriSign Class 3 Public Primary Certification Authority G5, has a certificate representation, just and this is it, and that's where now we've reached the top of the trust chain, because we've seen that the subject and the issuer are identical. If you look at the fields, they're identical, which means, okay, as we've discussed, this means it's a self-signed certificate. So the issuer, I've issued this certificate to myself, but the reason that's okay to do that is because we are a root certificate authority up here, which means that we are trusted implicitly by all the well-known browsers, right? So I know I'm repeating myself. I'm doing that deliberately. So what we have now is called a certificate chain. So we've got the ultimate, let's call this the leaf node. It has one intermediate parent, which is the VeriSign Class 3. Sorry, my apologies. It's the Semantic Class 3, right, which is the intermediate. This one, in turn, has a parent, which is the root parent, and that's the VeriSign Class 3 Public Primary Certification Authority, right? So that's our entire certificate chain, right? Now, and so this is the overall parent. This is I guess you could call it the grandparent grandmother of this HSBC one, and this one is in the middle. So hopefully we're getting there. Gonna push on if anyone's still awake. So basically, let's go back to what's happening on Humpty's computer when they receive this HSBC certificate, right? So first of all, what they do is they say, right, look at this certificate and look at the issuer name, right? Now it's semantic class 3 EVB SSL CA. Now, in order to validate this, I'm going to need to use a signature, and in order to do that, I need to find out what the public key is corresponding to this issuer, right? So therefore, where does that public key come from? Because Humpty's machine needs that public key in order to validate the signature. The answer is, when the bank sends their SSL certificate to Humpty Dumpty's machine, they also have to send this one at the same time. So they send the two together, right? That means when Humpty's computer is validating this SSL certificate, they have both of these in hand. So it's literally like having two documents in your hand side by side, and it's as simple as saying, right, well, the common name of the issuer for the HSBC certificate is semantic class 3 EV SSL CA. I'm going to look at my bundle of certificates that I have in front of me that I was presented, and I'm going to look up the one where the subject is semantic class 3 EV SSL CA, which is this one, and I'm going to read off the public key from that certificate, and bingo, I've got the public key, right? If I don't find that I have access to any certificates that HSBC have sent me along with my, in my initial response from them, if they don't send me a certificate with that matching name, the validation, it fails, and the certificate is deemed invalid, and then, as usual, the browser will proceed with warnings or whatever the case may be, right? But if HSBC have done their job and made sure that they send the intermediate certificate along with their own server certificate, then we can proceed, right? So the client browser is going to take that public key from the issuer, right? It's going to decrypt the signature that was sent, right? It's going to compare that with the hash of the certificate that it received, and if the two are equal, then this one, the server certificate, is validated, right? But it doesn't end there, right? Because this browser does not implicitly trust this semantic certificate, right? It doesn't have this one embedded into its trusted key store of golden, totally trustworthy, well-known certificates, right? So it needs to also validate this one, right, before it can ultimately give the thumbs up to Humpty saying, go ahead, enter your account details and knock yourself out, do whatever you want, right? So how does it validate this one? Well, it does exactly the same thing. Exactly the same thing. So it says, right, well, I'm now looking at this semantic class 3 certificate. Now, how do I know if I can trust this? Well, first of all, I'm going to look at the signature. Okay, fine. And I'm going to say, okay, who's it issued by? Right, so it's issued by common name, VeriSign Class 3 Public Primary Certification Authority, G5. Okay, so first of all, do I have a certificate like that in the chain that was sent to me by the bank? And the answer is no, because they only sent me two certificates. They sent me their server certificate and they sent me this one, the one I'm currently verifying. So, all right, let's look in my local, this is what Humpty's machine will say, let's have a look in my local list of all my trusted certificates, right, and see if it's there. Maybe Google Chrome have told me, this is one of the kind of the godfather trusted certificates that everybody in the world should trust. So he's going to look in that list and see, do I have any where the common name is VeriSign Class V Public Primary Certification Authority? And the answer is yes. At that point, fantastic. So at that point, what they do is they say, right, well, I've got that certificate in my key store. Get the public key, right, which is here. Take the signature, decrypt it with the public key of the root certificate, right, this one over here. And then, once again, hash this, as in hash everything that is not the signature, using the algorithm that it says here, so SHA-256 with RSA. And then, literally, compare the two. And if those are the same, then what that means is that that this certificate is a bona fide Symantec certificate, and it implies that the more to the point, that this public key here that's in the certificate does actually belong to Symantec, right? Now, the reason I say that is because once again, I could easily generate my own SSL certificate, with these details here, the corporation, blah blah blah, and I can include my own public key that doesn't belong to Symantec, belongs to me. So what we've done here is say, okay, Symantec, what these guys have done to get the signature, they have basically had to have the signature signed by VeriSign, and VeriSign are right at the top there in terms of the trust tree, to the extent that we basically all trust them. Now, a few questions probably emerging in people's heads, or concepts. First of all, the entire system depends on the trustworthiness of these root certificate authorities. So basically, if these are breached, if the integrity of these certificates is breached at all, then the whole thing does fall apart. And I think that's considered by some people to be something of an alarming scenario. But that's currently the best we have in order to achieve this kind of encrypted web traffic between browsers and servers. So that's really it. So you can probably tune out now if you're still awake and fed up with the sound of my own voice. But I'm just gonna sort of reiterate a few times just to kind of really hammer it home, right? So Symantec themselves, they have their own certificate that is issued by VeriSign, and the signature is created by VeriSign. So Symantec have basically, have all these details here about themselves. The issuer is VeriSign. They would have sent a similar procedure. VeriSign create an SSL certificate for Symantec. VeriSign would then hash the certificate they create and encrypt it with their own VeriSign private key, right? And that private key is super duper confidential, and it's basically locked behind, it's like Fort Knox to get hold of these things. But that's what they would do. VeriSign would hash the certificate that they've created for Symantec. They would encrypt it with the private key, and then that's the signature. Whoops. That's the signature down there, right? So then in turn, what that means is that Symantec can then use their certificate and use their private key to sign any other certificates on behalf of VeriSign. So as long as the end user accessing HSBC or whatever bank, as long as the end user trusts VeriSign, or more specifically as long as they trust the certificate, very signed Class 3 Public Primary Certification Authority G5, then any certificate signed by this certificate, or more specifically, signed by the public key corresponding to the private, signed by the private key corresponding to the public key that's inside this certificate, will be trusted, right? Now, if you think about it, you might wonder why we have these intermediate certificates, for example. So why don't we just say, why don't we cut out the middleman and say, HSBC, you apply directly, you have your certificate signed directly by this root certificate authority, right? Why is that the case? Now, these kind of questions I'm going to talk about in subsequent videos about, because it really comes under risks of compromise, different types of compromise, and steps taken to mitigate those risks. So yeah, that's for a future video. So let's take the use case once more, and I'm sure nobody's going to follow this all the way to the end. So Humpty Dumpty accesses HSBC, https hsbc.co.uk. HSBC web server sends back one certificate, their certificate, installed on their web server, and includes the digital signature for that certificate, sends it back to Humpty. Humpty's machine is going to use the public key inside that for subsequent establishment of a secure session. Now, in order to do that, it first needs to ensure that that public key does not belong to anybody other than HSBC, because if it's been modified and somebody else has inserted their own public key in there, then there's a big problem. So how does it validate that? Well, it looks at who issued this certificate. It says, right, look at the common name. Has HSBC sent me in the same response another certificate with this common name as the actual in their subject field? The answer is yes. HSBC sent both of these certificates in the initial response, and therefore what I'm going to do is I now have enough information to go ahead and validate this certificate against the signature. So I look at the signature. I take the public key belonging to that I find in the issuer certificate, which is this one here. I decrypt the signature, and then I hash the certificate, the server certificate, with the SHA-256 algorithm, or whatever is down here, and I compare the two. If they're not the same, then it means that the signature and this document do not match, and there is an issue. If they do match, then I can focus my attention on now validating the next certificate up the chain, right? Because the server certificate and the signature so far, they do check out. But can we trust the semantic, the intermediate certificate that have been sent? So they look at that one. Then they'll say, right, look at the common name. Is this in my trusted key store, right? Is this one of my hard-coded browser trusted certificate authorities? The answer is no. So we say, okay, in that case, first of all, we need to validate that this certificate itself really checks out as well, that it's been issued by the right people, right? For example, because a man in the middle could have basically issued their own certificate by somebody called Semantic with their own public key in there, right? So what we're going to do, we're going to look at the signature again. We're going to look at who issued the certificate. In this instance, it's VeriSign, Class 3 Public Primary Certification Authority, G5. And we are going to say, right, so did HSBC send me a certificate with that as the subject name? The answer is no, they just sent me two. But do I have this in my trusted root certificate store? So they're going to look in that store and they're going to look for this one and they're going to see, yes, we do. Okay, fine. So this one is signed by a trusted root certificate. Let's make sure that this signature does indeed correspond to something that has been signed by this root certificate, and if it does, then we're good to go, because I trust anything that's been signed by these guys. Okay, so we do, again, we use the issuer name, and we say, right, so I know what my root certificate is. I'm going to look up the public key in my root certificate, and I'm going to decrypt the signature down here, and I'm going to hash everything inside the purple box, and if the two of them match, then I can honestly say that that all the contents of this purple box are totally valid. They've been checked out, and they are good, right? In particular, let's just think, for a second, the public key is one thing, that man in the middle are always going to want to take an existing SSL certificate and just basically modify the public key, right? But if you change the public key in the certificate, you're going to change the hash. So if the signature and the hash correspond, and more to the point, that the signature can only have been created by the trusted certificate authority, then we know that this content itself has all been validated by VeriSign, which is a trusted root. And in turn, just going back to the server certificate down here, the signature, what the signature does is say, if the signature and the content check out, so if I look at my issuer, decrypt the signature with the public key of the issuer, and compare it with the hash of the certificate, if those two things are equal, it means regarding HSBC certificate, as per semantic, all this information inside this purple box is accurate. Totally checks out. The address is correct, the domain is correct, the expiry date is correct, the public key is correct. It all checks out. The question is, that Humpty's machine asks is, well, is that good enough? So, so that's what, just because it's checked out according to semantic, is that good enough? The answer is no. So we have to go one step up the certificate chain again and find, and we do another signature validation here to check this signature and say, right, as per VeriSign, this signature verifies that this public key actually belongs to semantic, right? And therefore, so all this content is valid as per VeriSign. Now the question is that good enough? And the answer is yes, because we trust these guys, the trusted certificate authority, to do all the due diligence required to make sure that these guys are who they say they are, right? I'm flagging a bit because I've been talking way too much. I know this is a bit verbose. I know it's a bit complicated, but the key point is that, to get the whole idea of the chain across, and what else are the key points? That normally, so the signature is created by the public and private, it's created by the private key of the parent certificate, and it's decrypted using the public key of the parent certificate, and it's appended to the end of the child certificate, right? And then this parent-child relationship is really, really important. And you can see it, and you basically, so when a client receives a server certificate from, can be HSBC, can be Gmail, can be whatever, what that client does is that they're going to receive the server certificate, and they're going to receive also one or more intermediate certificates in a chain, right? Now, this is an example of a three certificate chain, right? But you can have chains that are longer, you can have chains that are shorter. But the concept is exactly the same. The client will traverse the chain, going from issuer to subject, looking at the private keys and public keys. Stop there. It definitely will not be looking at the private keys of the intermediate certificate authorities. That's a very important point. The private keys are only known by the certificate authorities themselves, but the client will traverse. It will traverse the certificate chain using and at each step it'll use the public key belonging to the parent certificate to validate the signature in the child certificate, and so on, until it finds a certificate that it implicitly trusts. So if you like, the orange line is where we traverse, right? So we traverse up to here, then we traverse up to there, until we find the orange line has nowhere to go, because the certificate, the trusted certificate, is signed by itself, right? And I guess, what would happen if I, let's say I created my own self-signed certificate, right? Or let's say HSBC created their own self-signed certificate. What that means is, instead of, so let's say down here, right, where we have issuer name, right, and subject name, what if we just said issuer name down here is HSBC, right, is in the same details here, just like up here the issuer and the subject are the same, right? So down here, HSBC, say the issuer is HSBC, the subject is HSBC. We're not going to bother paying semantic money to get this this Ssl certificate signed. We're just going to create our own, right? What happens then is that Humpty Dumpty, right, he's going to get this certificate, right, and it's going to say, okay, it's been signed using the bank's own private key, not Semantic's private key, the bank's private key. So the signature is going to be the hash of the certificate encrypted with the bank's private key, and it's obviously, as usual, it's going to contain the bank's public key as it always does. So the first part of the validation, which is going to be, well, as always, look at the issuer of the certificate. Fine, it's HSBC. Find the public key corresponding to that issuer, right? And that's the HSBC public key, and check, basically decrypt the signature and make sure that the public key, decrypt the signature and make sure that the hash and the decrypted signature are the same. Fine, that works perfectly fine, right? The hashes add up, etc., etc. But the problem is, your certificate is still not trusted, because it has not been signed by a trusted certificate authority. It's basically been signed by HSBC, and your browser has not been able to traverse a chain of certificates leading up to a point where the ultimate parent signer of this chain is someone that the browser already inherently trusts, right? So what you could do, what the user could then do is say, well, add this HSBC entity as a trusted certificate authority in their own browser, and that would mean next time they access HSBC, their browser wouldn't warn them. But that kind of defeats the object of the whole thing. So self-signed certificates, I mean, I can do another video on it if you want. Just leave a comment. But I think I've kind of described it in as much detail as needs be. So that's a very, very long video. I hope it made sense. Leave any questions. If you have any questions at all, please leave them. Any comments, any requests for future topics, etc., etc. Thank you for watching, and I will see you in the next video.